Next is the temperature. There is the air temperature, right, that we measure with thermometer. And that temperature that we usually measure it with, we put a thermometer in the air and we see what's the reading. That's called dry bulb temperature. That's the regular temperature that we are used to. There is the wet bulb temperature. That is going to be a new concept. So what is the wet bulb temperature? You wrap on the thermometer, you wrap a piece of cloth or a piece of cotton that is basically a little bit wet. So there's water in it. And so as the air goes through, if the air is not 100% humid, if the air still can take more water, 40%, 20%, he is not 100% humid. He will take water out of that wicking material, that cotton swab, that whatever clothes you are putting. And so as a result, the temperature of that thing will drop. So the thermometer that has a cloth on it will measure lower temperature than the one that is just basically a regular thermometer in the air. And that's what we all experience in the summer when we get a little bit sweat on our skin. That sweat basically when it evaporates, it makes us a little bit cooler, right? And how cool? I mean, you can just apply the first law of thermodynamics and you figure out that the amount of energy that involve evaporating that film, whether that's in your skin or it's the cotton's clothes on top of the thermometer, the amount of energy it takes is related to the evaporation, and that will drop the temperature. So the wet bulb temperature will always be less than the dry bulb temperature. I mean, the limiting case is when the wet is equal to the dry. Why? Because he cannot evaporate anymore. Why? Because he's 100% humid. So if he's 100% humid, then his wet bulb temperature will be less than the dry bulb temperature. But as long as he's lower than 100%, he will evaporate. And the drier the air, if it's like 10% humid, there is a lot of room for the water to evaporate. So it will evaporate, and the wet bulb temperature will end up being very, very low, right? So the difference between the wet and the dry bulb temperature is a measure of how dry the air is. The more the difference between them, the drier the air. And if they are the same, then the air is 100% humid. Okay, so dry bulb temperature, wet bulb temperature. Okay, because of the evaporation from the wicking material. And so they do this in a little bit more professional way by putting the two thermometers next to each other. One of them would be dry and the other one will have this wicking material on top of it, and they will basically let the air go through by a fan. He's saying here you can do it with a fan with a battery, but there is other design where you just basically hold them and roll them like this. They are sitting on an X and they rotate them, and so as they rotate in the air, the one that is just a regular thermometer will measure the dry bulb, and the other one that has a wet cloth on top of it, he will end up measuring the wet bulb. Alright? So different design in order to get this, but you need water sitting on the thermometer reading the wet bulb, right? And that's what he's saying here. Owing to evaporation, he will get lower temperature. So now let me introduce the psychrometric chart. That is like the best thing that ever happened to the psychrometric analysis. Basically, all the calculation that we did and more that we're gonna do next is gonna be a piece of cake using that chart. So this chart basically is all the equation that we talked about simplified in a cartoon. Okay, so for example, what is this? Some of you might have seen this chart, and some of you it's their first time. This chart is in the table in our textbook, at the end of the textbook. Okay, in English unit and S unit. And I remember when I was undergrad, in order to have very good reading in this chart, and the nerd I was, as I told you, I actually printed this on a really huge piece of paper, and I will take it to my exams with me, and I was so proud of it. Like, You know, I was like, it's really, really big. I'm doing, but the screen is so small. It was like really huge chart, right? Forgot, was it on A2 or A1? You know, but a really big chart. It was by Carrier, so I was really proud of it. So this chart has those lines. Those are the phi line. What is phi? Relative humidity. So 100% line, 50% line, 10% line, and so on, right? So you put a point over here, and you'll be able, if the point exists over here, you can tell. For example, if your point here, you'd say, ah, that area is 100% humid. If the point is here, that's 50% humid. So what is the y-axis and the x-axis? That is the dry bulb temperature, the regular temperature that we are used to. And on the y-axis, that is omega, right? The humidity ratio, the kilogram water vapor per kilogram dry air, which is also translate to B vapor. Remember the equation? The omega is 0.622 B vapor over B atmospheric, or B mixture minus B vapor. So for that translation to happen from omega to B vapor, this chart need to basically be saying what B mixture did they use to convert, right? So in order to convert from this to this, they will tell you this chart is for 1 atmosphere. And if it's not, it's for different pressure, then they will tell you. They will tell you this chart is like for 2 atmosphere, or... Okay? Very good. So then, knowing omega and the dry bulb temperature, we can get the phi, right? If we know omega and dry bulb, and also if we know the dry bulb and the phi, we can go ahead and read omega. Very good. Now, what are those lines? Those are the wet bulb temperature lines. So again, there are two temperatures, dry and wet. And so if you know the dry bulb and the wet bulb, you intersect them, and you basically say, I am here because my dry bulb was this much, my wet bulb was this much. You can basically get yourself the state. Once you find that, it's like the steam table. You know how we can, using the pressure and temperature, we can find everything. So knowing dry bulb and wet bulb, you find everything else. Knowing the phi and W, you can find everything else. Knowing any combination of those two things. And you can do this with the equations, but it involves a little bit more calculation. And then this chart is basically instantaneous because it's based on a graphics interface, really. This line, a little bit vertical line, not really totally vertical, but a little bit, that is the volume per unit mass of dry air. Volume of what? Volume of dry air or volume of water vapor? Free quiz. So which one? It's the volume of all of them because they share the same volume, right? They share the same volume and they share the same temperature, but they don't share the pressure. So this is the specific volume of the air, the meter cube per kilogram of dry air, if you read that number. And it's also the specific volume of the water vapor, but in a weird way, because it's the meter cube of the water vapor per unit mass of dry air, rather than per unit mass of water vapor, like what we are used to call the specific volume. Okay, and finally, there is a scale over here that will tell you the enthalpy. Again, per unit mass of dry air. Everything per unit mass of dry air. Okay, and so how do I read this chart? Well, if your point is here, you know, like for example 50% and the wet bulb was this much, you find yourself over here, and now you are like, what is my enthalpy? You go up on the wet bulb line, which is almost the enthalpy line, and you read on that scale what is the enthalpy, right? So he's gonna elaborate more in the next few slides. So that's what he's saying over here. If you know your state, you can read your dry bulb temperature. If you know your state, you can read your omega. If you know your state, see, this is super easy and very convenient too. If you know your state, you can get your dew point. How can I get my dew point? What happened in the dew point? we did cool the air and the water vapor all the way until what happened? Until we hit 100% humid air. That was the dew point. But so we are reaching that line at the dew point, but are we reaching that line this way or that way or this way or what exactly? Well, to reach the dew point, you are cooling at constant what? We are cooling the air at constant omega. Why? Because we are cooling it at constant B vapor, right? So when we cool the air slash water vapor mixture, we are not adding or taking water vapor, not yet, not until we hit this point, right? So it's constant B vapor. And so if you, wherever you are in the chart, if you want to find what's your dew point, and that could be a really nice quiz or a homework problem, you just stay here and you go all the way to this point. This is your dew point. This is the temperature where you start dropping water. Okay, and I told you those are the constant humidity line. And if you want the enthalpy of the mixture, you just go up and you read your enthalpy. Mixture enthalpy per unit mass of dry air. So it's H air plus omega H vapor. Okay, very good. So this again, this chart is very convenient, but it's a little bit, there's a little bit of approximation in this part, but it's pretty cool, actually, pretty very useful. All right, so he's saying wet bulb and dew point temperature scale. It's the dew point when you come like this, right? So when you hit here, that would be the dew point. And the wet bulb temperature. So how do we read the wet bulb temperature? This is a little bit confusing. So those are the constant wet bulb temperature, right? Those are the constant wet bulb temperature. So if we are here, for example, like here, we are here, and I would like to find out what's my wet bulb temperature. This line, all this line is one wet bulb temperature, okay? And so you can read it in the chart. It also happened to be when the point is here, that happened to be the dry bulb that come over there. How is that possible? Because imagine if you are existing at this point, what this point represents here. That's 100% humid air. 100% humid air. So at that point, the dry bulb, which you can read easily by going vertically down, remember the x-axis is the dry bulb. So this point have a dry bulb that you can read it going down. And it also has a wet bulb that is exactly the dry bulb because it's 100% humid. Right? Actually, let me go to the chart and I explain this much better. So here is the chart. Of course, the chart is not only 100%. You got yourself the humidity 100%, 90, 80, 70, all the way so that you can get good resolution. And here is the omega, and you can see how the number are tiny, 0.002, 008, right? Kilogram water per kilogram of dry air. And those are the specific enthalpy, and you can see they are almost the same as wet bulb. So now what is the wet bulb temperature? It is those lines. So if we are here at this point, okay, 30%, he said it's 30% humidity and whatever that omega number is. And you end up saying, okay, I'm sitting here. What's my wet bulb temperature? Well, it is this big line. And that big line over here, that line has a 20-degree wet bulb temperature. How did we find it's 20? Well, it's written 20, but also when you go to that line, you go down there and it's 20. That line, see that line, that's a wet bulb temperature of 10. You go up at the end and you go down, it's 10. And so on and so forth. Why is that? Because for each one of those lines, that's 30 wet bulb temperature. I bet if we go here down all the way, we will end up hitting 30. Right? Clear? Because at 100%, the wet and the dry become the same. And that page that we skipped, that is basically saying you can read the specific volume. And why do we need the specific volume? Why is that useful? Well, in order to calculate the air from the velocity, for example, or convert the volumetric flow rate to the mass flow rate, you need the specific volume. And so the example over here, this example will show you how useful it is to calculate things from this chart. So he gave us 30 degree and 25. I don't need even to know which is the dry. I bet the hotter one is the dry and the colder one is the wet. So 30 and 25, and he will ask for all kind of things. Give me the phi, give me the omega, give me the enthalpy, right? So how can I find 30 and 25? So 30 dry, right? And 25 would be here. That is the dry pulp, but it also, that would be the wet. So I will intersect the wet at 25 with the dry that is 30, and that is my point. And I go here, I read the phi, and so, you know, that's why, again, I made this chart really big when I was a student so I can read easier. But anyway, it's like what, 68, and you go and read the omega on the other side, it's 0.018, right? And you go and read the enthalpy. So 67, okay, not 68, and 0.181. Right? It's very hard to read on this chart, but again, if you really make it bigger, you will be able to see those tiny scale. Right? Point is, it was piece of cake to convert from dry and wet to all the other guys. You can do it with the equation, but it just takes a lot of time. Alright.